Okay. Cool. Okay. Good afternoon. Thank you very much for coming to this talk, and thanks to the organizers of JavaDay of this really amazing event. I'm really impressed. This is my first time in Ukraine, and I just really am kind of blown away by what's going on here. So the community is terrific. So I'm very happy to be here. I'm talking about today. Today, what I'm talking about is slightly different from what the program suggested. So, in the program, I was hoping to present a talk about that was quite specifically targeted on stream performance. So this is a talk which is also about stream performance, but it's rather more general. So there's quite a lot of an introduction here to the general idea, both of streams and especially to what we should be doing when we measure performance, because everybody's very keen on measuring performance. Everybody thinks it's a great idea, but actually, it's really quite difficult, and people often don't understand the circumstances under which we should be doing it. So I'm going to talk, so there are some preliminaries to this talk. And first of all, I'm going to introduce the particular case study I'm going to look at. And that will take maybe about 20 minutes of the talk, something like that. And then I'll get on to looking at this case study and considering how, what affects its performance, both as a sequential stream and as a parallel stream, and what we can do to improve it. So before I go on to the introductions, can I just check how many people were at my talk yesterday? Okay, so I have to be really careful about not telling all the same jokes again. That was really what I wanted to know. And I also have to say that for some people who were at my talk yesterday, a little bit of the introduction will be familiar. So I'm going to repeat that a bit, but I'm hoping that it won't take too long. So the introduction of who I am is the same as it was yesterday. I haven't changed since then. I'm the things it says at the top because I can't find one single word to describe myself, and I'm a member of those community programs, and I'm the author of a couple of books, or I'm the co-author of one book and the author of another book. The generics book is a really old one. I'll tell my standard joke about that. It's absolutely the best book there is on Java generics. And I can't say the same thing about I can say I think the same thing about the book on lambdas and streams. So everything I'm going to tell you today, or nearly everything I'm going to tell, a lot of what I'm going to tell you today, I learnt when I was writing the book on the right there, because I had to think quite hard about streams. The book doesn't have streams in the title, it's all about lambdas. Actually, the subject matter of the book is all about streams and not lambdas. And I had to think quite a lot about performance as well. I'm also the maintainer, if you can call it that, of the Lambda FAQ, but it's not very well maintained now, so I kind of skip over that slide. It's still a pretty good place to go if you haven't been using lambdas until now, as an introduction to them. So the background I was talking about that I'm going to use to motivate the talk is in these three parts. So you can see it's going to take a bit of time to explain a little bit about Java 8 streams, and as always, I have to check how many people are actually using Java 8 streams in their everyday work. So it's more than yesterday. It's about half the audience, and I'll go a little bit faster. But I'm hoping that it will make sense to you even if you haven't been using them. I'm going to talk a bit about parallelism and why we're interested. I'm going to talk a bit about micro-benchmarking. And then the main part of the talk is about the case study there. So sometimes I say that this talk, which is it's like any time I talk about performance, and I found the same thing when I was writing the performance chapter for the book, is like it's like a sex education talk in school. So you come along really wanting to know about the subject, about performance, and all that the teacher will tell you is why you shouldn't be interested in it, and why it's not important to you, and why nearly all of the time measuring performance is a really bad idea. So unfortunately, I'm going to, you get bored with an anatomy lesson, and I'm going to do that, and then I'm going to go on about why you shouldn't take any practical interest in it. So let me run through then these background items. Streams in the first place. Why do we want streams? Well, we want streams because for two main reasons, the two reasons on there. My perspective, and I think probably most people's perspective, has changed during the lifetime of Project Lambda, as it was called, which brought Java 8 to the world. To begin with, a big motivation for having streams was to bring the fork join framework, which allows automatic parallelization of code, was to bring that to the surface and make it usable. The fork join framework has been there since Java 7, but it was quite difficult to program. And as we're going to see, streams gives you a very nice interface to it, user interface, I mean, and makes it very easy. So really, the slogan in the second bullet point, which says explicit but unobtrusive parallelism, was the big motivation. And you're going to see when I talk about this, you're going to see that actually the opportunities that you have for using automatic parallelization are perhaps more restricted than we might have initially hoped. But the first bullet point, to bring functional style to Java, I think will be the one that actually will be much more long-lasting. So the intention is that we're going to the major use case of streams in Java 8 and onwards is to replace loops for aggregate operations. So forgive me the people who already know about this stuff, but I'm just going to run over it quickly. Previously, where we've written code like this, we've got a bunch of people here, or a list of person objects, and we want to accumulate the names of the cities that they live in, provided those cities have less than 4 characters in them. So actually what Brian Getz, who's the Java language, who's the architect for this, for the Java 8 Lambdas project, used to say he would flash up a piece of code like this, and he would say to the audience, tell me what this does. And he would say, like, you've got 5 seconds to do it. And you're sitting there kind of scratching your head, and you're thinking, oh, there's a loop there, and then there's, then we're getting a property here, and now we're testing it for length, and then we're adding it to short cities. What's short cities? Short cities is a set. It's quite indirect and difficult to understand. And we're going to replace code like that. The idea of using streams and bringing functional style to Java is to replace code like that with code like this, which initially looks much harder when you first see it, but I think in the end will seem to us much more natural. So here we're doing something that seems like a kind of fairly, once you know how to read it, you say, okay, we're taking this list of person, and we turn it into a stream, whatever one of those things is. I'm going to describe it as values in motion. And these values will then, each one of these values will be mapped to the city that the person lives in. And then each one of those, now city objects, which are what are getting sent on to the next operation, they will be filtered, and the ones will be dropped out that don't satisfy that predicate. And now we've got a stream of city objects which we're going to collect into a set. And once you learn to read this stuff, it actually reads an awful lot better, I think. So we say that the claim is it's going to be more concise, more readable. Very importantly, the operations are composable, so it's easy to build up much larger operations from much shorter ones. Yesterday, I used the analogy of a Unix pipeline for that effect. And importantly, still very importantly, it's very easily parallelizable. So what we can do is we can just write parallel stream there instead of stream. And hey presto, we get parallelization. So I'll go on to talk about that in a moment, in a bit more detail. Here's my picture of what sequential streams look like. Once again, I apologize to people who were here yesterday. My idea is that since it's quite difficult to explain what streams are to Java programmers, because we're used to collections and we're used to iterators. So I say a stream is a little bit like an iterator because it's lazy. It's only when you actually start the terminal operation that pulls values down the stream from the source through the intermediate operations. And my picture of what's happening here is, if you think of the x's and y's, not so much as single values, but actually they're going to be like sequences of values. So there, x0, well, x0 in this case was a single value. It got transformed to a y0. It passed the filter, and it passed through to the reduction. I'll talk a bit more about reductions in a minute. And here comes another one. This one also gets transformed, but it doesn't pass the filter, and so it doesn't get passed on, and so on. So there are many kinds of intermediate operations besides map and filter, and there's a huge collection of reduction operations. I talked a little bit about those yesterday. I'll talk a bit more about them today. But it's in these operations, the intermediate and the terminal operations, that a lot of the interest of the Stream API resides. So the practical benefits of streams are the functional style that I've shown there will affect virtually all collection processing. So we're going to stop writing code like we saw on the left-hand side, pretty much, and instead we're almost always, not always, but nearly always going to write code like we saw on the right-hand side. So that's going to be a big change for Java programmers. It's a difference in style, which is going to affect almost everything that we do. And so that's going to affect nearly all collection processing. In certain situations, writing parallel stream instead of stream will also be really useful. So it would be nice to say in certain situations and leave it like that, because they're not that common. But the fact is, everyone cares about performance. Right? So this is actually a big motivator, and one of the reasons why they felt like they had to provide automatic parallelization in Java 8 was because otherwise people would lose interest in Java. I mean, so this was a big sell. And what's the reason for that? Well, the fundamental driver for getting automatic parallelization into Java was this graph, which I guess probably quite a lot of you have seen. It's taken from a very famous article called "The Free Lunch is Over" by Herb Sutter, and I noticed it was published. I was looking at it recently. I noticed it was published almost exactly 10 years ago. So 10 years ago, Herb Sutter, who was much more awake than most of us, he's a very well-known author in the I think in C++ area. He noticed that whereas Moore's law still holds, so that's the green line here, we're getting the prediction that Moore's law said, which was that there was going to be roughly double the number of transistors per surface area every 18 months. The corollary that we'd all learnt, the thing that we learnt would follow from that, which is that the speed of processors would double every 18 months. That stopped happening around about the early years, around about the 2003, 2004. And he saw this coming. And this was at a very early stage. And there are all kinds of reasons why this line here, which is the processor speed, is not going to rise again. And those reasons have to do with the fundamental physics of how the semiconductors that we use work. And it's got to do with fundamental limits like the speed of light, which we're not going to get the better of in any time soon. So I sometimes say that when the transistor was born, it had two fairies standing at its shoulder, like in the old fairy stories, a wicked fairy and a good fairy. Maybe it's at the baptism, I think. So at the baptism, you get a blessing and you get a curse. So the blessing came from Gordon Moore. He was the good fairy at the birth of the transistor, and he said, "You're going to have so many descendants, you won't be able to count them." It's like Abraham. Your numbers will be as the stars in the heaven. and that indeed is. That's turning out to be the case. As we know, there's just transistors absolutely everywhere, and there's no sign that they're going to be reduced in number at all, and that's going to slow up. I'll come on later to talk about who the wicked fairy was that stood at the other shoulder of the transistor. So because the number of transistors is going to continue to increase, and their speed isn't going to continue to increase, I think this is probably ordinary stuff for most people. What we're getting is now increasing number of cores on the processors that we're using. So here's a picture of a 2-year-old, it's more than 2 years old now, Intel chip with 10 cores that you can see here. A huge amount of the area of the chip here given over to cache because actually synchronizing values between the different cores is a really big problem. And because the cores are so much faster, the main reason is because the cores are so much faster than the memory bus that you can't afford to transfer data from main memory all the time. The caches are very much faster, and the hope is that what we would really like to have happen would be we'd like to get a different thread resident on each one of these cores. And when we've got the kind of data that can be processed through recursive decomposition, that is if the tasks that we're performing on the data, say like, I don't know, image processing, for example, or weather forecasting or something like that, if the tasks are independent, then each thread can work away on its own core, and they won't have to talk to one another, and we're going to be able to split the work down and get it done and get it done in parallel, and obviously therefore very much faster. So the real challenge to the Java designers was how can we make this happen without forcing you to actually write the code explicitly that it implements a recursive decomposition. That's what you have to do if you're going to use the fork join framework, and it's not that difficult, but it's not that easy either, and it's not going to be something you want to do every day. It's a lot harder than just writing parallel stream. So here's my visualization of parallel streams, and the idea of this is that if we could split the data down, instead of processing it serially, what we could have different threads processing the elements in parallel. And I've deliberately in this one I've actually managed to force myself not to have them all move at the same time. X0 and X2 are working first, and they do something, and it's quite disorganized. So internally you can't be sure of the sequence of events. But the Stream API is very, very cleverly designed to ensure that even though these things all happen in a different order, they'll get reassembled into the right order at the other end. It's supposing, for example, you're dumping them into an ordered collection. If you got them from an ordered collection and you're dumping them into an ordered collection, then they'll automatically get there in the right order, even though what happens internally is not necessarily going to be so ordered. Okay, so I've talked about streams a bit. I've talked about parallelism. My last preliminary before I go on to the case study is to talk about measurement and micro benchmarking in particular. So again, apologies to anyone for whom all this is familiar. The question we would really like to find out when we want to know what the effect of code changes are on the performance of our programs is what we would really like to do is we'd like to run a controlled experiment that would actually really evaluate under production conditions, if possible, the exact difference. Well, actually, that's really difficult. That's extremely difficult to do, and the reason it's difficult to do is because we've got to reproduce production conditions is very hard. We're not usually allowed to just experiment with production systems, obviously. To reproduce production conditions, we have to have a typical hardware setup. We've got to have characteristic loads on the system. We've got to have a characteristic environment in terms of the network performance and the database performance, and so on and so on and so on. It's really very hard to do, to set up an exact mirror of your production environment. So we don't do that. Instead, typically what we do is micro-benchmarking, which the idea of that is a controlled experiment where we try to make sure that everything is held the same, thinking here about science, how you would do this if it was science, then you would run a controlled experiment. Oh, where have I gone to? Sorry, excuse me. I'm in the wrong. Sorry, excuse me. I'm in the wrong application. There we are. Got it. We would run a controlled experiment in laboratory conditions where what we would do would be to have a very much simpler environment. If we held everything the same and we could just observe the differences that result from changing the code, well, that might do just as well. And then actually we could do some of the things that scientists really like to do, which is to publish the benchmarks and to make it really clear what the environment, what the hardware was, to allow peer review of our experiments and to treat them basically like scientists treat their data. Unfortunately, we're still quite a long way from that. We have to be really careful in this situation about something called the substitution effect. This is a psychological effect whereby when you have a difficult question to answer, it's very, very easy to substitute a much easier one and answer that question instead. So when I was first writing this talk, there was an election in Britain at the time, and I thought, well, there's a really obvious example of the substitution effect at work in the British election. Because when you want to elect a new government, what you're thinking about is which party has the best policies to build the kind of society I would like. You know, I don't know, with the right sorts of freedom and the right sorts of welfare and all this kind of thing. That's obviously a really difficult question to answer. So a much easier question to answer is, which guy looks, or woman, looks best on television? Right? That's actually quite an easy question, and most people actually decide how to vote on the basis of a substituted question. So the substitution effect is quite a problem here, and it's very easy to say, oh, well, look, my micro benchmark has produced the right result, so that obviously must be what I'm really interested in. And micro benchmark, even if you did manage to get the right answer through micro benchmarking, that's to say you got a true answer, you still have a big problem. Because even to get to the point of getting a good answer through via micro-benchmarking, you have to overcome a lot of difficulties because the dynamic runtimes frustrate measurement hugely. So, for example, I mean, in the JVM provides two measurement methods, current time millis and system.nanotime, and they're both of them significantly flawed. The granularity of current time millis is dreadful, and system.nanotime, its implementation varies radically on different hardware platforms. The just-in-time compilation can occur at any time, and you can't control when it's going to happen. In the middle of your measurements, garbage collection may kick in, and of course that will distort your results considerably. If it kicks in for one experiment but not for another one, you have to control that external factor. After the code has been run for some time, Hotspot has been profiling it, and it says, oh, we've got a hot method here. We better optimize it, and so that's yet another disturbance, another perturbation to your results. And indeed, after a while, something may happen to force Hotspot to de-optimize it. Maybe you had a monomorphic dispatch, and now a new class has been loaded, and it turns out that actually monomorphic dispatch isn't valid any longer, and it'll have to back out of that optimization and go back to megamorphic dispatch, and that again will really disturb your results. So there's a lot fighting against you. The worst of them is dead code elimination. That seems like quite a strange thing to say about an optimization, that the worst one is actually a really efficient one. So dead code elimination, obviously, is the idea of that is that the Hotspot compiler can detect when your code's never going to be used, and it just won't execute it. So that's really a problem, because almost all the time what we're trying to do is we're trying to calculate new values. What we want to measure is the speed of the calculation, not the speed of storing the values. But if we don't store the values, then Hotspot will detect that we're not storing them, and it won't execute the calculation. And if we do store them, then typically the cost of storing them is going to completely dominate over the cost of the calculation. So we're really in a cleft stick as far as dead code elimination is concerned. It's a big problem. The only real way of getting around it is to unpredictably store a very small sample of the results. And then the compiler can't throw your calculation away because it might be needed, but equally, if you don't do it very often, then the cost of the storage won't actually dominate. So this is really quite a hard problem to solve, and we've got these benchmarking libraries which have actually thought about, the authors of this have thought about it quite a lot, and they've solved that problem. Or they've gone a long way towards doing it. So I recommend anybody who's doing micro-benchmarking to use one of these libraries. So there's Google Caliper, and there's the Java micro-benchmarking harness, which is the one that I use. And that was written by people in the Oracle team, and it's very, very good. So you've got to do all this stuff, and you've got to make sure that your results are going into what JMH calls a black hole, and you've got to and there are various other safeguards. You read the documentation on these, and you realize how many pitfalls are available to you. And then you run your experiment. You make sure it's statistically meaningful. You publish your results, and you make sure they're peer reviewed. And that's all you have to do to make micro benchmarks work. So I think this stuff is really important. I think it's important to talk about this because quite a lot of the time you see these blog posts which say, I measured this operation, and it was like 5 times as fast as that operation. And you don't see the code, and you don't know really what was measured. And fundamentally, results like that aren't worth a great deal. So that's my sermon on performance measurement over. Now on to the case study. So my case study that I used for the book was a little-known option of grep called grep minus b. So the idea of grep minus b, what I thought I would do was to imitate in a functional style the Unix utility grep with some of its various options. And most of them weren't very challenging. But grep minus b turned out to be quite an interesting one because grep minus b says that the offset, if you say minus b, you will get prefixed to each matched line the displacement in bytes of that line within the file. So that seems like that's not going to be very difficult. But the problem the problem that you immediately come across when you think about getting a stream solution to this is, the kind of really obvious one is, I'm going to have to keep a running total of the number of bytes. I mean, every programmer immediately has a solution jump into their mind which says, okay, get the first line, find out how long it is, that's the total so far, get the next line, find out how long that is. Anytime I get a match, I'll prefix the running total that I've reached so far. But that isn't going to work for functional style code, such as we write with streams, and we'll have to have a look at what will work instead. So here's my sample code. I included this because in English, I'm sorry, but okay, so there's a little introduction to English literature, or Iranian literature, actually. This is the Rubaiyat of Omar Khayyam. I don't know if it's well known in Ukraine. It's quite well known in the UK. And I love this verse. It's obviously about how you can't go back in time and you can't put your mistakes right. The moving finger writes, and having writ moves on, nor all thy piety nor wit shall bring it back to cancel half a line, nor all thy tears wash out a word of it. But as somebody practicing, it was written by a fantastically accomplished and polymathic Persian mathematician. He was an astronomer and a philosopher and a lot of other stuff as well. And he was also a poet. But what I like to think is that he was obviously a functional programmer in the making, because this is obviously all about immutability. You can't change anything once you've created it. I don't know why that never gets a laugh. So here's an example of, maybe it's just a really feeble joke, but I like it. And I keep on using it. So here's an example of grep minus b applied to this verse of the Rubaiyat. And you can see that with the second line, I'm matching against W, against an uppercase W followed by a T, somewhere followed by a T. And you can see that the first line that matches it is this one, which is 44 bytes in, because there's 44 bytes of the first line. And then the last line, this one, also has a W followed by a T, and that's the start of that is 122 bytes in. So supposing I've got a program to do this, and I've got a program to do it, and instead of it working on 4 lines of the Rubaiyat, it works on a 10 million line file. So now I'm going to pay attention to the question of measuring the performance with a view to optimizing it. Now, what I said at the start about this being like a sex education talk kicks in now, because the first question I'm going to ask is, why shouldn't we bother to optimize it? So one reason why we shouldn't optimize it is because we don't have a problem. And actually, it's commonly said, one of those things that every programmer learns is premature optimization is the root of all evil, and that sort of thing. So there's actually very good reasons for not optimizing code. How would we know if we did have a problem? People often find this really quite a difficult question to answer. If the code is running too slow. What's too slow? I mean, you could always make your code run faster, right? If you don't have a target, you don't have anything to optimize against. And if you don't have a target and somebody just says, if your manager just says this code is too slow, you can speed it up a bit and say, well, it's still too slow. So actually fixing non-functional requirements like performance targets is as important when you're involved in the development as fixing functional requirements. So the first thing to do is to make sure that you really do have a performance target and you're optimizing against it. And very importantly, when you reach that performance target, you stop, because otherwise you're going down a road for which there is no end at all. So here's a possibility then. I'm imagining that the program that I have in mind, which calculates grep minus b, I'm imagining that we did have a target for it, and we're not achieving that target. So what else might be the problems? Typically what people will do in this situation is they'll say, fine, let's put the profiler onto it, let's put a Java profiler onto it and see what's happening. But actually that's not the first thing that you should do. The first thing that you should do is to see whether there's a problem somewhere else in your system. There might be the problem might not actually be in your VM at all. It might be somewhere else. So there could be a problem, but not in your process. Here's an example of that. So I'm going to. I've got here a program that does this. It's called Not Your Process. If I run this. Not my process. Oh, if I run it on the oh, that won't work very well. Oh, and it won't work at all if I don't mirror. Sorry. So let's get that code up. So here's my code. Oh, here will come my code. Right. So if I run this on the verse of the Roubaix app that I showed you, it gives me the right result. And if I run it on a big file instead, like the file of lots and lots of lines, I can actually take a look and see what's going on. It is actually running really slowly. The first thing I should look for is, if I can find it. Oh, here we are. Somewhere, no, okay, let me bring up the performance monitor then on this machine, activity monitor, and let's have a look at the CPU. The CPU load, here it is, right, okay. So what we're seeing there is, and of course you can get the same kind of thing through your performance monitor on your Windows system. What we're seeing there, do people know what the difference between the red and the green is? Okay, so red is kernel time. It's basically time the operating system is spending managing hardware. It's housekeeping time. Green is the time it's spending in user space where it's actually getting the work done that you want. Typically, you don't want kernel time to be more than about 10% or so of your total load. And here it's obviously absolutely enormous. So to make a point, what I did was to create some code which was definitely going to have a big problem. Let me see if I can find it now, because I've succeeded in losing my my project. Here we are. Okay. So the problem with this code is, I really fixed it. I'm reading from a file reader. And the file reader is defined as, I'm reading actually each character from a file reader, and the file reader is just an input stream. It's a file input stream. So basically, I'm reading character by character from the disk, and this is obviously a very extreme case, and it's completely stupid. But it shows that you can't depend on. In a sense, the problem is with the code here, but it's not really with the code. The problem is with the system. So you might well find that you've got sort of ridiculous amounts of red activity because there's a network problem, for instance, or because it's spending a lot of time swapping between processes. So you're looking at it here from the system level rather than from the code level. So let's suppose then that let me stop this pointless activity and go back to. And go back to the slide. So we'll suppose then that we've fixed that problem, and we've found that the problem is not in our process. The problem is in our process, and it's not that the OS is struggling. So this is I'm talking about these things in the order in which you should look at them. We're going from outside inwards. So the first thing is to ask, do we have a problem? The second thing is to look at the system as a whole. The third thing is to look at the VM. There's a problem in our process, but it might not actually be in our code. Of course, in some sense it's in our code, but it might not really be. The next example I'm going to show you, it's not actually in our code at all. So what's the biggest consumer of CPU time within the VM that isn't our code? It's garbage collection. That's the big user. Let's see an example of how you would detect that and what you might do about it. So let's see. Somehow I seem to manage to get onto the wrong project all the time here. Let's just go back. Right. Mirroring and. Okay, so let's go and take a look at this. That's not what I want that. Oh, one. Oh, sorry. Okay, let's just get this right. So, not my day. Huh? Sorry. Oh, that's really not what I wanted. See, demonstrations that never fail to put you wrong. So what I'm going to do now is run a project. Hopefully I'm going to get a project up, and if I can get the right one, then I'm going to run this and see what other problems there might be and how we could detect those. Come on. All right. So I've still not got the right project. It's loading this one last. There's a kind of rule about this stuff, which is you should just unload everything from your machine first. Well, I didn't do that. Okay. My apologies. See if we can get there finally. Okay, right. So here we are. So I've got a program called Not Your Code, and if I run this. Right, we are on, aren't we? If I run this, Not Your Code, then you see what I'm doing in this case is you can't just about make it out. I'm going to log I'm going to send the garbage collection logs to a file called notyourcode.vgc. So that's really the main difference here. So let me run this, and it'll write to the. It's going to work on those on that big file that I mentioned earlier, and why is it saying that? Oh no. Doesn't matter, I'll allow. Yeah, and you can see it working down here, and then we can go and take a look at the garbage collection logs and see what we can see about it, because this is the next thing that you should check. So first of all, you should check if you've got a target. Secondly, after you've got a target, you should check, is it your process? Thirdly, if it is your process and it's the VM, then what you should do is check the garbage collection logs. So let's go and have a look at the garbage collection log now, since the process is finished. See if I can find somewhere. Right. Okay, so I'm having a hard time today. Okay, so this actually does look like a garbage collection log, doesn't it? Let me just check that I've got the right one. Okay, actually, I'll just cut things slightly short because there's some characters in there which can't be read by my log analyzer. So I'm just going to get rid of those. I just know that now, and because you've been very patient with me, I'm not going to drag this out any longer. So I've cut those funny characters out, and the analyzer I'm going to use is something called HP meter. The HPJ meter, sorry. So HPJ meter is a log analyzer. It's free, so that's something to be said for it. It's not very sophisticated, but it's going to be good enough for our purpose here. If you wanted to do something a bit more serious in production, you would probably get one of the numerous good paid-for solutions. I was put in a plug for one called Sensum, which was written by a performance expert called Kirk Pepperdine, who I've worked with and who actually taught me most of what I know about this stuff. So if we look at the log from HPJ meter, we see that although you can't read it here, probably, what it says down here is it's the ratio of full GC to GC. Now this is red. I mean, we've actually got quite a lot of red on here. Like the percentage of time in full GC is 23%. That's ridiculously high. If we look at if we just take a little look at the duration of the GCs, we see since the red here are all full GCs, this is absolutely terrible. The vast majority of your GCs should be partial GCs. Clearly, the garbage collector here, again for the sake of demonstration, has been really badly detuned. So the idea of a generational garbage collector is that it should collect only the areas in which newly created objects have been stored, because most of those die very young, and therefore there isn't an awful lot of work in collecting them. But in this case, instead of that, we're doing lots of full GCs, and full GCs are very expensive. So it's clearly a mess, and in fact, if we look at the heap usage after GC, you can see that it's all over the place. So you can learn to read this stuff, and it's a really good idea to do that, just on a precautionary basis. Well, once again, I really, I kind of mucked about here, and I sort of cheated. I mean, if I bring up again the window which shows what the VM options were here. I showed you before that I was writing the GC log, but what I kind of skipped over was the fact I've set the survivor ratio to being a ridiculously high number. If you're used to seeing garbage collection, you'll know that that's absurd. Basically, I've said there's going to be no survivor spaces, which means there's going to be no collections in young space at all. Everything will be immediately promoted to old space, and what that means is that every collection has to be a full collection. And so, once again, I mean, in order to make a point, I've kind of bent the stick a long way, and I've made it clear that you can't depend on a problem in your code. There's no point in going and profiling this code until you've checked out stuff like this. So we're almost at the point where we've eliminated all these different problems. We're not quite there yet. Oh, we are actually. So, am I on the right? Oh, I'm on the right one. Okay, so let's just get through these. So what I've done is I've checked out that there was that the problem was in our. I've checked out that it had a performance target. I've checked out the problem was in our process. I've checked out that it was in the that it's in the VM, and assuming that it's not garbage collection, finally I can go and take a look at if it's not GC that's using all the cycles. Now I can consider optimizing. Okay, so before I go and optimize, I'm going to understand the code a little bit. I said that it was quite difficult to imagine a solution where you would have how grep minus b might work if you weren't going to use an accumulator. So here's a very quick outline of my solution for grep minus b using what's called a collector, which is a terminal operation on streams. So the idea is that we're going to build. What we want to do is we're going to build a representation at the end of the program, which will be. This is a linear data structure, and the idea is that it will contain. For each line of the code, it'll contain two things. I mean, at the end, initially it's going to contain just the length of each line. I've got 4 lines here, and the last the third field there contains the length of each line. And what I want to do is I want to build that up and accumulate into it the total displacement. So the idea of any problem like this is to think of a partial solution. And this data structure here is, in fact, it's a partial solution. So you can imagine working down from the top. If we start off with each line individually, then we can work down, and at this point we've got 2 halves of the problem. And so we're going to combine those. It's kind of obvious how we're going to combine them. I'll show you it in detail in a moment. But it's also obvious how you can get to this partial solution from the start. So I could start off with a data structure that looks like this. Each line is in a. You could think of it as an array list. I didn't actually use an array list, and you can combine two of these things together in a rather obvious way, because it's quite clear that if you've got if the initial displacement of this one is 0, but its length is 44, then the displacement of this one is going to be 44, because that's clearly the start of the line. And if its length is 36, then we now have a total for this half of 80, and we can add that onto the displacements on that side. So in this way, you've got a solution without an accumulator. That's got by just kind of merging things together. So there is something called an accumulator, but it's different from an accumulator that would calculate everything, because part of this solution says this is how we're going to combine the partial solutions that have been worked out by the different threads. But if a thread is working on its own, there's no problem about having an accumulator. So this is what the code would look like for a single thread, where we really don't care about having the same hot field over and over again. We have a thing called a supplier, which produces an empty data structure, and then we add a line into that, and now we can take another line and add that onto there as well. So a single thread can work like this, and threads working together will work as I showed you on the previous slide. So here's my graphical picture of how it works, which has got a little bit out of order from the rest of it. But you can see how we're going to combine these things together to calculate the total displacements. So let's go and take a look now at what the profiler shows us when we try and run this code. So I'm going to use NetBeans for this because the profiler on this just works for me. Well, that's what I found. I tried others, and I'm not a great expert in profiling. So. Have I got the right one? grep-b with Klepter. Yes, that's the one. So it doesn't take very long to run, and then we'll just take a quick look at the CPU snapshot at the end of it, and we'll see something which probably oughtn't to surprise you too much. I think, if you think about what I've been talking about, the cost of the different operations on parallel streams. So let's get the snapshot and take a look at it. So all the time's going in main, obviously, and it's in there, and we're running it sequentially. Everything appears to have been called from the collect operation. I don't know whether I think I mentioned this time that streams are lazy, and they don't actually, the actual processing doesn't begin until the terminal operation is called. So everything always appears to be a result of calling the terminal operation, which is collect in this case. So we can see that we can go down to that. Essentially, we're iterating over the source here, and actually, if you look in there, you can see that a huge amount of the time has gone into this buffered reader method, has next. So actually, what's happening is we're spending most of our time, even on this sequential solution, we're spending it getting I/O from the disk, because I stored that big file on the disk. Right. That's going to be a killer for any attempt to go parallel, because if you're only dripping the data into the parallel pipeline, then it doesn't matter how fast how fast the different threads on the pipeline are, the bottleneck is always going to be the data. So let me go back to the slides now, because thank goodness I finished these incredibly error-prone demonstrations. I'm glad to get away from them, I can tell you. Let's get past this. So the question is, what's wrong? Possibly very little is wrong, because actually this thing doesn't perform that badly compared to grep-b. But the question is, could we improve it by going parallel? And the answer is, well, I'll skip over this, because actually there are problems that I don't really want to talk about here. But the biggest single problem is this streaming I/O. So the streaming I/O is inherently serial. And parallel streams need splittable sources, or else you're not really going to go parallel. Here's my little demonstration of how the splitterator works, which is the source of a parallel stream. Basically, it takes your data set and it splits it down. So you've got a splitterator here. Well, initially the range of the splitterator is the whole. Initially, the range of the splitterator is the whole data set. The splitterator splits the data into two, and then it splits it again, and so on, until eventually you get to the point where you've got a set of data, and each thread, now the threads are shown in different colors, and each thread can iteratively process the segments of data corresponding to each splitterator. For this problem, I invented a new splitterator, which was actually something new to the JDK, although it's now been incorporated into the JDK. So it's quite nice to have had an example from the book that actually made it into the platform libraries. In this case, what I did was I took all the files from disk I/O, from the disk, and I moved them into a mapped byte buffer, which is essentially the same thing as getting them into memory. So the map byte buffer allows me to just randomly look in the file. I split the file roughly in the middle, find some midpoint, and then just go looking for an end of line character. The implementation in JDK9 is a good deal more complicated than this, but that's the basic idea behind it. Now the splitterator coverage can be split, so we get the split that I showed there. So if I did this, then I now can get something useful out of parallelizing grep minus b. So the collector, which I showed you, is the basis in which those splits can be merged again. The line splitterator, which I just showed you, is the basis on which they're split. And now we can focus on the really difficult, the expensive part, which is the regular expression matching. Luckily, regular expression matching is actually expensive enough to justify the overhead of splitting and then merging again. And this is what you have to look for if you want to go parallel with stream code. So it's actually much better than it used to be, because also the collector doesn't need to compute the index any longer, because we can put into each split we can put the displacement within the file. So basically, if you can find the right solution, you're going to do really well, and parallelization will really work for you. I mean, in this case, we've got the sequential stream is better than the iterative solution, and the parallel stream gave gave very good speed up. I mean, perfect speed up would be 4 times on a machine with 4 hardware threads like mine, but 2.5 times is a big gain. I had to do quite a lot of thinking to get this to work, and you may be in that situation. The question about when to go parallel, when you can really take advantage of the ability to parallelize your work, is actually quite a complicated one. So you've got the workload of the intermediate operations has to be great enough to outweigh the overheads of splitting, which is about 100 microseconds. I made it a bit less than that, but that's what the Oracle team say. That overhead goes into initializing the fork join framework. And besides the initializing the fork join framework and the splitting, then concurrent collection at the end is liable to be very expensive as well. So the collection actually has a significant overhead too. And you also have to take account as well, when you're thinking about whether to go parallel, that some of the intermediate operations aren't as parallel friendly as regular expression matching is, as in this case here. So you might have, for example, you might decide that you want to, as an intermediate operation, you might decide you want to sort all the elements of the stream. Now, the only way you can do that is by accumulating the whole lot of them. It's a complete barrier to parallelism. So sorted is kind of an example that's kind of the worst example of that. But some others are quite surprisingly bad. Like the Oracle team always quote limit as being remarkably difficult to parallelize. You think, well, the limit operation, that can't be too hard. All I want to do is just really to be able to take the first 50 elements. But if the 50 elements are coming down a disordered parallel stream, then finding the first 50 isn't really that straightforward. So we've got problems about splitting. We have to have efficiently splittable source, like I showed you the line splitterator allows. I have to say, you don't often have to do that. Most of the collections come with their own splitterator. Well, all the collections come with their own splitterators. And you can actually make a pretty good guess about which ones are efficiently splittable. So, for example, array list is obviously efficiently splittable, but a linked list clearly isn't very efficiently splittable, if we're thinking about finding the midpoint and splitting it. You don't often have to write your own, and you don't often have to write your own collector either. But you need to be aware of what's involved when you're thinking about this. So you need to think about the overhead of the efficiently splittable data, the overhead of the intermediate operations, and you need to think a bit about about collectors as well, because you're going to take the data that comes from the stream and you're going to dump it back into a collection, and that actually can cost quite a lot. For the non-thread safe collections, like to list and to set, where you're dumping the data back into an array list or a hash set, then those things, the performance will be dominated by the accumulator, which will be, for an array list, for example, it'll be the add method, that kind of thing. But if you've got parallel streams, then the framework has to manage concurrent access to these non-thread safe containers. It's a very clever thing to do, but there's an overhead involved. If you're collecting to a map or to a concurrent map, then you have to take account of the fact that map merging is really slow and map resizing is really slow. So one of the things I learned was that you really want to try to optimally size your data structures that you're collecting into at the start. So in the real world, it's not even as simple as I've been saying now, because in the real world, you may well have other competitors for the cores. So the fork join framework is written on the basis that it will allocate enough threads to use all the cores. But of course, you may have other processes. You may have other competitors for the fork join pool, and you may have other processes that want the cores. And that's going to really, damage your performance quite a lot, especially if it leads to a lot of swapping between different threads. So you have to take that into account too. This sort of thing isn't going to work on an application server, for example. I mean, that's not an optimal scenario. So the fork join pool assumes by default that it can use all the cores, and that's not necessarily the case. And it also assumes that your intermediate operations are going to be CPU bound, because if they're spending a lot of time going off and doing I/O, then you're going to lose a lot of the benefits of parallelism that way. Okay, so I come to just in time, I come to the conclusions of the talk. The first one is the discouraging observation that we've really all been wasting our time, because performance mostly doesn't matter. So like nearly all of the time, if performance matters to you, then you're probably not going to want to be looking at the kind of question that I've looked at here. It's very interesting, and I mean it's a lot of fun to look at, and everybody wants to look at it. But usually it's not really the central issue. But if you must look at it, because if you can be as disciplined as I've suggested in narrowing down on your problem, then these are some useful conclusions. Sequential streams normally beat iterative solutions, not always. Parallel streams are quite a narrow case, as it turns out, unfortunately. They can utilize all cores, but you need to fulfill these conditions, and those conditions are quite demanding. So we're really looking at a fairly kind of niche set of use cases. Okay, so that's the story. I've got some resources that are useful to look at. If you're interested in this stuff, then the first one is a web page written by Doug Lee, who was responsible for the fork join framework primarily. Guidance about when to go parallel. The second and third one are resources from Alex Shipalev, the author of the Java micro benchmarking harness, which are extremely useful, because he's really the go-to guy for the kind of problems I've been talking about. And of course, this resource is absolutely invaluable to anybody who wants to know about lambdas and streams. So thank you very much for your attention. I think I'm out of time, right? No questions? No. I'm around. If you want to talk to me about any of this stuff, I'm around for the rest of the day.